Okay, next up we'll have John Stone talking about HPC libraries and frameworks. Take it away, John. Thank you.
Good afternoon. So my name is John, and today I'm going to tell you a little bit about HPC libraries and frameworks. I'm sort of an atypical presenter of this kind of topic because I spend most of my time developing application software, and while I use libraries and frameworks for various things, I'm not an expert in any of the specific domains that you probably are. So my talk today will sort of cover the use of these different libraries and frameworks, what they're good for, what some of the state-of-the-art technologies that they employ can be, and what the benefits of those technologies are for your performance or the flexibility of these codes. And because, over the years I've had to write libraries for my own purposes to overcome portability barriers and things like this, I can give you some insight into what to watch out for when you're either using a library or considering the different benefits or costs to the various options that are available to you. So this is sort of the overview of the topics that I'm going to cover, and I'll try to keep it relatively quick. So the major reason people use libraries is so they don't have to reinvent the wheel. Of course, how many people here have ever even learned how to do a transcendental function on their own? Do you know how to do a sine or a cosine the hard way from writing code from scratch? How many people know how to do that? Very few. Back in the old days, to use a computer, you'd actually have to know how to do all this stuff for yourself. So you can imagine that it didn't take very long before people figured out that this is really a costly pursuit and we should not have to do this over and over again. And so we began developing subroutine libraries, as they used to call them, or math libraries and things like this, solvers. And they began with sort of the fundamental math functions like sine, cosine, transcendental functions, things like this on computers. And they eventually evolved to encompass things like data structures, high-performance hash tables, different things like this, containers, libraries for processing and creating and managing graphs and things like this, and of course then different algorithms, very higher level things. Sorting algorithms, of course, were very fundamental early on, and this grew to encompass almost anything you can think of. So one of the benefits of libraries in the modern context, particularly right now when we're seeing a high rate of change in the development of computing hardware, is that libraries are a great way to abstract the differences between competing hardware architectures. So, from a certain perspective, if you have a standardized library interface, you don't really care what kind of hardware it's running on, as long as your code is still able to run on that hardware, perhaps being abstracted by some existing library. So, for example, if the majority of your code is linear algebra, so long as there's a library for doing that on the target platform you want to run on, the rest of the details may not be that important to you. Your performance may be provided primarily by that library, and the rest of the unique aspects of your application may be the way you're assembling it at a very high level. And so if you can find libraries that do these things for you, that's a tremendous time saver, and it makes it easier for you to retarget your applications to different platforms over time. So another thing that's nice about libraries, by and large, you can use the same libraries from most languages. So if the library is written in C or Fortran, while it may be somewhat inconvenient, it is usually possible to call the library from any of the other languages. So, for example, I've written Fortran code that was then called from C++, and I've written C++ and CUDA that then called Fortran or were called by Fortran code. So you can cross all those language boundaries a number of different ways. In the case of very high-level languages like TCL, Python, other scripting languages like Perl, Julia, various other sort of dynamic languages, all of these other languages have mechanisms for creating bindings for external libraries so that you can call them conveniently within those dynamic languages. So as an application developer, of course, as I described, what you're really after is you're sort of filling a gap with the library. Either you have a need for some algorithm that you don't know how to implement yourself, or you don't have the time to implement yourself, or you're trying to address some sort of performance bottleneck, and then you go out and you search for the available libraries and algorithm frameworks that can cover this gap. By using somebody else's library, you are benefiting from the time and energy that they spent developing that code. You don't have to write the code, learn the minutia of the hardware that it's implemented on. You don't have to perform all the development and testing and maintenance of that software going forward. You can rely on the work that somebody else has done for you. In the case of some of the state-of-the-art hardware that we have today, this cost is significant. And as the hardware gets more and more complicated, it will become increasingly important that you exploit all the opportunities available to you to save that time. Another reason to use a library is some algorithms are a lot more tricky than they look like they are. And so one of my favorite examples of that are random number generators. I don't know if you know much about the history of random number generators, but this is so tricky to the average person that there have been random number generators widely distributed as part of standard math libraries that were basically wrong for decades. And people didn't realize this, and it harmed the results of large-scale Monte Carlo simulations. So something as simple as a pseudo-random number generator can be dangerous if it isn't properly vetted. And one of the things you're getting out of using a professionally written and maintained library is that you're not personally responsible for that. You can trust that somebody else has done it, or at least you should, maybe trust but verify. You should go look for a publication where somebody has evaluated the performance or behavior of the library. Again, you can exploit hardware-specific optimizations. You probably, if you've been watching the news, you see in state-of-the-art CPUs and GPUs, we are now seeing new arithmetic units and extended instruction sets and things like this that many of you probably have never really looked at programming by hand yourself. Some of those things are tricky to use, and even if they weren't that difficult to use, they do evolve over time. So there's an ongoing, never-ending cost that if you write code by hand, you have to take that onto your own shoulders, and you have to carry that with you in the further development of your application. Whereas if you use somebody else's library where they've invested that time and energy, you get that benefit essentially for free. Another benefit of libraries is, particularly in the ecosystem of sort of mature, well-established libraries like linear algebra, these things have evolved to have a standardized set of application programming interfaces. So if you go look at any of the implementations of BLAS, for example, that do things like matrix multiply, if you go back and look at the earliest versions of BLAS and the state-of-the-art versions, there is a compatible calling convention that goes back 20, 30 years and persists to now. So that means an old piece of code could use a brand new library today and immediately reap the benefit from state-of-the-art library implementations without any noteworthy changes to the original code. That's a great thing. Another thing that lets you do is it lets you swap in one library for another, perhaps written by a different vendor, a different source, and then you can compare the performance or the accuracy or other attributes of these different libraries and make a decision about which library is the best for your particular application. So some of the examples, Google is pretty powerful. I do not need to list every library for you, and I don't really think it's important for me to show you the minutia of how to use any particular library because you know more about your application domain than I do. So, but just to give you a flavor of what exists, right? There are libraries for basic math functions. So one of my favorites, and one of the reasons I highlighted CFEAS in bold is CFEAS is kind of a fun thing. If you've never seen what goes on inside the guts of a math library, that one is open source. And you can go look and see how sine and cosine and tangent and all the other functions are implemented. After you look inside that library, you will come away with a great appreciation of what work goes into these numerical libraries and why they're hard and why it's tricky to make them fast on state-of-the-art hardware. But another thing that it's useful for is you will also start to understand where there are opportunities, maybe performance is left on the table, and you could actually get better performance doing something special for yourself than exists in any library on Earth. And so you should keep that in mind too. There's a flip side to these things. If you use a library, you may leave some performance on the table unknowingly. So being able to look at how a library is implemented under the hood, to me, is a great aspect of the open source codes that are out there. So CFES is such an example. There are other special libraries like SVML. There's a short vector math library by Intel that solves the special purpose of being able to do your transcendental functions on vectors of operands at a time. So that's a nice special purpose library. There are other libraries like the GNU Scientific Library that has sort of the huge collection of other just useful routines. So beyond those, like I described earlier, a huge area of existing work with libraries is in dense linear algebra. That's probably the most mature area of computing in terms of library use. It goes back decades and decades, and it's very well curated. The libraries generally are all of very high quality. All the ones that survive today are good libraries. All the bad libraries no longer exist. They're gone. And so that's great for you. And so what you're choosing among these different libraries are basically upon their other attributes, whether they're open source or they're commercial. Do they cost something? Are they free? Are they for a CPU, a multi-core CPU? Are they for a GPU? Are they for a heterogeneous combination of those things? Or are they for large-scale distributed memory message passing across a huge machine? So that's what distinguishes each of those different choices. When you get into things like random number generation, this again, it's dangerous. Unless you know what you're doing, don't do this yourself. Use a library that's been trusted. And also watch out for things like one of the time-honored books in computing for beginners in the old days was a book called Numerical Recipes. For many years, they had very weak examples of random number generators included in the book, and so. But you don't have to be reading these things out of books because there are libraries that do an excellent job of this, and you can just use them. You shouldn't have to write this stuff for yourself. Of course, fast Fourier transforms, and again, you have choices for different types of hardware platforms. So, as I said before, linear algebra is really where the most action has been with libraries. Or if you could type into Google linear algebra library, and you'll probably get 30 pages of results, more than you could ever count. And it's because there are so many variations of these problems, and the different libraries are trying to shave off a little bit of overheads, or they're trying to make certain types of problems easier, or they specialize in one kind of solver or another, and those things have led to a huge panoply of different options. You also have, again, the interoperability between the different libraries. So by and large, you have some sort of standard API, and then you have extensions to those for the different specialized variants. So you might start with an API for standard BLAST routine, and then if they want to do that on a GPU, now you have two different memory spaces. So they might have made some changes to how you allocate memory or how you pass a matrix in to indicate, is this on the host, is it on the GPU, where does that data live? So those are things you have to be aware of. So with BLAS in particular, with dense linear algebra in particular, you have a number of libraries that are these are the only ones I'm going to really talk about by name because they're kind of worth knowing about because they're sort of the fundamental bedrock upon which everybody else designed their linear algebra systems. So you have basic linear algebra subroutine library, BLAS. And it has different, as they call them, levels, which are the different types of linear algebra, arithmetic, vector, vector, matrix, matrix, matrix. These have different flop costs and memory reference counts, which you can look up. They don't really implement solvers. Then you have a higher level library called LAPACK, which basically does all of the different types of solver routines. So you can do matrix factorizations, linear equations, solvers, all this sort of stuff. They work at a higher level. So they are built on top of what the subroutines in BLAS really provide. You could have written your own solver using BLAS, but you would be better advised to use something that's in LAPACK because the experts who work on these solvers day in and day out have sort of engineered these things to make the best possible use of whatever underlying routines exist and their high-level understanding of the target hardware. And the same is true, going to scale-up packs, and now you're talking about running those solvers across a big distributed memory machine with MPI, and they have extended all these APIs to allow pointers to memory buffers that are on different nodes, things like this. So you describe the problem on a much larger scale, and then the solver library will run this for you. And so you can incorporate these libraries in your application, and you don't have to repeat all of the engineering and testing that the teams of developers that wrote these tools did. So when you're choosing libraries, you have a lot of different metrics in front of you. I would argue that the most important is going to be, in the long term, things like accuracy, correctness, how robust that library is to tolerating various kinds of faults, or what does it do under an error condition? Does it report the error? Does it silently fail? One of the things we often experience with HPC or supercomputers is an old phrase called the tyranny of large numbers. You test your code on a small computer or a desktop or a workstation or maybe a handful of nodes and everything's fine. But when you run on thousands of nodes, it fails. And not just once, but it fails over and over and over. And you can't understand why this was, quote, working fine on my little machine. And it turns out to encounter some extremely rare exception, which happens on large node counts. And so things like that are a consideration. How well does the library scale to huge problem sizes? Can it handle an input matrix that's a fractional terabyte in size? This is something that not every library or every implementation of a library can handle. People are always updating their code, but until they have actually run something on real hardware, you don't actually know if it can scale to that size. So this is something you always have to watch out for. I would say once you know that the library works and it meets your accuracy and robustness needs, then of course everybody wants speed. And from then on, that's the thing that most people are interested in. I would say over a longer time period, the use of sort of standard or compatible APIs is an important aspect of what you're doing. If I invest the time if I'm writing an application and I invest the time to incorporate and test the use of some library that performs something for me, I want to know that I have maintained this ability to swap in some alternative implementation. If I am using a library that's too off of the mainstream, it's got a specialized API that's highly differentiated from the other libraries of the same sort, I better get something in exchange for that. So if they're giving me a strange API, then I want more performance, right? That's a trade-off because you're going to incur the maintenance and testing for this special API that this special library is using. So that comes up more with things like GPUs than it does for CPUs, but you should keep that in the back of your mind. Why is it using a different API? Is that going to be a long-lived differentiation, or is it a short-term phenomena? And what does that mean for me if I have to run my code on 3 different platforms? Do I have to use 2 different APIs or 3 different APIs? I'd rather not. So keep that in the back of your mind. Another thing you have to think about is, will that library get along with whatever else is in your code? One of my personal favorites was when I was porting my molecular visualization and analysis application to run on big machines with MPI. I discovered that there were conflicts between certain MPI implementations, which will remain nameless, and certain parsing libraries, which will also remain nameless. And it's because they had global symbols that conflicted with each other because they used another sort of parser generator tool to write both of those libraries. They had conflicts inherent inside those libraries. This is something you won't know until you go and actually link your code. If you have things like global name collisions, 2 things have the same subroutine name, that's something that's probably not well documented if it's an internal subroutine and not something that was meant to be used by the caller. So I've experienced that in my own work. This could happen anywhere. Another thing you have to watch out for is a library thread safe? Does it do anything that would be bad if several threads call the same library at the same time? Do they have some hidden internal state? I have used standard template libraries that were not thread safe, and we started trying to read a file and it became gibberish, or the code crashes, or various other things. or you have a library that has some internal static data or global symbol that it's again an undocumented detail of implementation that you won't find out about until something bad happens. In the modern context, are these libraries compatible with your other compiler directive systems like OpenMP or OpenACC? One of my favorites with CUDA is, does some other library code assume it owns the GPU, and does it go do things that are destructive to my application? I already have a CUDA context. I don't want the library to create another one, and I sure don't want it to delete mine. Or I don't want it to gobble up all the memory and prevent my other algorithms from using the GPU effectively. So the behavior about resource sharing and context creation and releasing those things is something you have to watch out for. But of course, there are cool things that you might get mostly for free. Library can give you things like intra-node parallelization, where using the same API you might have used for a serial code a few years ago, running that now with a modern library, you might automatically use all the CPUs and all the GPUs with no effort on your behalf at all. And this would be great savings in time. Similarly, as I said, libraries like Scalapack, maybe that one's built in, but you have to have a little buy-in. You have to help the library do what it does. But a lot of these have hooks where you can do some sort of distributed memory problem solve with maybe a very minor amount of buy-in on your code. So another consideration when you're choosing your libraries, there are a lot of open source libraries and there are a lot of commercial libraries, and they're not equal. Generally speaking, the proprietary libraries are serving some higher purpose, which is either to sell hardware. That's one thing they're used for. They allow the hardware to actually achieve what the marketing people say is capable of, right? And so you hear about some brand new piece of computing hardware and they say it does X teraflops. Well, let me tell you, your odds of getting X teraflops are low. To get those teraflops might be very hard, and it only does that for certain conditions, but the people who make the hardware have the greatest understanding of what it takes to achieve that, and their libraries have the greatest propensity to actually reach those peak marketing numbers that you've been told. You may never be able to reach that number if you have to go it alone without the proprietary information that the engineers inside that company have. Libraries that are commercial but they're not hardware specific, they live and die either by convenience or by offering some unique feature that isn't generally available in the open source libraries. Like they may specialize in solvers that are very difficult to require things like arbitrary precision arithmetic or other specialty features that may not normally be available in your run-of-the-mill libraries. And those commercial libraries, because they're not funded by a hardware vendor, their existence is predicated on providing some other value beyond the open source stuff. So the ones that are still in business are probably serving some particular sub-community very well. And then, of course, the open source ones become the bedrock. You should be no worse than the free ones, right? The free ones, you should definitely not be using a library that's any slower than the stuff that's out there that's open source and free. So the concern you have then is the different restrictions that these things may place on you when you use them. I'll get to that in a little bit. So here's a great example, though. This is, I just took this off of one of Intel's current web pages. So they're advertising the value of their BLAS implementation that's in the math kernel library that Intel ships, and they're showing it on some state-of-the-art Intel 56-thread chip. And they're comparing their performance with MKL versus OpenBLAS and Bliss. Now, I don't know anything about OpenBLAS or Bliss personally, but you can see that MKL is substantially faster. And, it's so this is the value of MKL for Intel is they are providing an application developer a way to achieve a much higher average performance on their particular target hardware. They know everything there is to know about making their chip fast, so you're unlikely to beat them on their chip. But their library isn't free. You have to spend money for it. And if you want to run it on a big machine, that the amount of money might be significant. So you have to keep that in the back of your head. So you might need or want to keep compatibility with the other libraries so that there's an option that is no cost for people that don't have any money to spend on such libraries. Another example here is 3D FFT. So FFTW is a very highly regarded FFT package, and it has a bunch of advanced technologies in it for auto-tuning and things like this. And one of the things that you'll see that's kind of interesting about this example space, Intel's showing the performance of their 3D FFT compared to FFTW in a problem regime where FFTW doesn't do very well, which is a small problem size regime. If I go back to the previous slide, you'll notice a phenomena here, right? All these slides, in fact, you'll note Intel didn't start at a matrix size of 4x4. They started at 256. That probably tells you that all the numbers to the left are basically nearly zero performance. And so this is an area where all libraries have trouble. So keep this in the back of your mind as we talk more. Small problems are difficult to extract peak performance on. You don't have as much runtime to amortize startup overheads and a bunch of advanced technology. And so the left hand of the chart is the hard end. That's where but that's also, if you really want strong scaling, you do care about the performance on small problems. So keep that in your mind. If you run on a 1,000,000 node machine, you decompose some huge matrix into tiny little pieces. Eventually, that left-hand side of the chart is what your single node performance is representing. So, what are the issues with libraries? Now we get into two words: libraries and frameworks. So, in my mind, a library is a collection of already written subroutines or functions. They are canned. You have no influence about what they contain or how they operate. So you can call them, and they do what they do. And the only inputs you have are the operands that they work on. You can't really influence the internal workings of those things. But the benefit of that is it's pretty straightforward. You're calling their code, but you're in control. You're running their code, and it does what you tell it to, and that's all there is. Frameworks are another sort of a more modern programming idiom. And the idea of a framework is it isn't completely canned. There is some additional dimension of flexibility to the software that combines something that they wrote with something that you wrote. And the two things together then are a better solution to your problem than a canned library routine would have been, or that what you wrote by yourself would have been. And so there is some capability here to allow you to specialize that library or the use of that library to give you better performance or a more application-specific use of that tool than would otherwise be possible. And so some of the examples that are out there that I think are noteworthy are like PETC, which does all sorts of differential equation, PDE solvers, things like this. A lot of the AI stacks that are out there I would think of as being a framework. You don't just call some completely canned library. The programmer is providing little bits of code that get sort of merged into those stacks, and that's where they get the secret sauce. They're pulling your code into this huge amount of machinery to extract the performance of the hardware, but you're getting your application specialization, what kind of data you're operating on, the different math that you may have to do to precondition it, and so on. One of the ones that I use a lot, that I actually like a lot, is NVIDIA does. So I do a lot of 3D visualization, and one of the things that we want to do is high quality graphics. And for that, we want to do ray tracing, and ray tracing is a particularly performance demanding technology for computer graphics, but it allows us to do very high fidelity rendering. There are canned ray tracers. I've written my own. So I wrote my own ray tracing engine. Intel has a canned ray tracing library. And optics, what's interesting about it is if you take any other existing renderer, it will always be written with the mindset that the implementer of that library took when they wrote it. It'll implement certain shading features and not others. It'll implement triangles, but perhaps not spheres. Well, for what I do, spheres are important, so I want spheres, right? So using something that's a framework, I can extend what they wrote with something that I wrote. So if they didn't have spheres, I just add them myself, and now I have spheres. Good day for me. And then if I maintain the part that they gave, I'm getting very nearly the peak performance that the hardware under the hood is able to provide for this task. So it uses, machine code or very carefully written internal JIT compilers that generate a sort of a merged piece of code that take pieces of my code with pieces of their code and run them together, and I get performance that I would probably not be able to achieve as an outsider that doesn't know the minutia of how the hardware works. So that's really great. The one cost of a framework is that, generally speaking, you're ceding some control to the implementation of that framework. You as the programmer may not be in complete control of how everything works. So optics is a great example of that. I give optics all of my little code snippets, and it jits them together and assembles them and builds a piece of code that mixes my code with proprietary code. When I want to run it, I have to ask it to go. And it has a built-in runtime system that, once I say go, it's hands off, and I have to let it do its job. I gave it the conditions for doing that job, but it is in control of the program flow from that point on. And so you're giving up a little bit of that control when you use frameworks. Template libraries. Now, how many people here are doing C++? Wow, not very many in this room, just a handful. Well, hopefully some others are, but one of the things that's cool about template programming, so compared to other languages, C++ being object-oriented and becoming gradually somewhat more modern, has type generic ways of writing subroutines, so that, or as we call them, templates. So you can make a templated function that takes arguments whose type you don't even know when you wrote the code. They could be arbitrary. So you could write a routine, for example, a vector that holds a bunch of objects. You don't even know what the type of objects are when you write the container. It could be anything. So it makes it very easy to build large, complicated pieces of code using these templates. And another thing that's interesting about templates is using some tricks that I won't go into much details about. There are things called template metaprogramming where you can combine templates together, and you give the compiler has an opportunity to do optimizations that are not possible with a conventional library, because it has both the point in the code where you're calling the template, where you're instantiating that template and you're telling it, these are the data types I'm operating on, these are the classes and objects that I need you to work on, and here's all the inputs. All of the information needed is available to the compiler at the same time, so it can do optimizations that would otherwise be impossible with a normal library. So this is pretty cool. So you should keep that in the back of your mind. This is used to good effect in template libraries, like, of course, a famous one with C++ is STL. That, lots of things use STL, but STL is sort of normal computing. Maybe a more numerical example is Eigen, which is a linear algebra library. NVIDIA has several different template libraries that I'm pretty fond of. One of the things that I like about those in particular is they're header only, so I don't have to compile and link in yet another library, so my link line doesn't have 300 libraries on it. These are distributed just as header files, and I can pick and choose little bits and pieces that I want out of those. And they do things like GPU sorting, they can do parallel prefix sum, they can do various kinds of reductions. They are extremely fast. They have all the knowledge and hardware optimizations that are possible. And because they're template libraries, you get this extra level of compiler optimization beyond what you would normally have with a typical compiler and a canned library. So I'm really fond of those, and they're super easy to use. So I like telling people about those. So, one of the other motivations for you to use libraries is to get access to state-of-the-art hardware and algorithmic advances. So just to give you an example, I'll show you one in a second here. So using a standard API, so this presupposes I have a standard API like we do for BLAS, and I just want to drop in a different BLAS implementation without actually changing anything in my application. Why would I do that? Well, maybe I want to use an iterative solver that is supposed to be fast because I heard about it at supercomputing and I say, wow, that sounds good to me. I want my code to run twice as fast. And some hardware vendor, like in this case, NVIDIA's got some newfangled hardware, like these tensor cores that use half precision arithmetic. And if you don't have the free time to figure out how to write iterative solvers that use half precision to good benefit, you can rely on the geniuses at University of Tennessee, Knoxville to do this for you. And so they have written, for example, a BLOS implementation that exploits, a LAPACK implementation that exploits these iterative solvers instead of using direct solvers. So the direct solver is the bottom line. So that orange line is what you get if you run a normal direct solver on the GPU hardware. And the other three lines are what you get when you use these mixed precision solvers that use an iterative approach on the same GPU hardware. Look at what a huge performance delta there is there. Now, the average person doesn't even how many people here even know how to write an iterative solver, right? So maybe one. I saw one guy put his hand up and then he took it down. Okay. So one guy feels comfortable doing this for himself. The rest of us are really quite happy that others have done this and we can just use it. So this is great. So you have a combination of really state-of-the-art hardware, and you have somebody has taken a library conforming to a standard API that every tool is already using, and they have taken advantage of this using the hardware and a new algorithm together. You get a tremendous speed up. So that takes you from about 6 teraflops to 24. How many people want a factor of 4 for free? Okay, yeah, I thought so. So that's a great outcome for very little programmer effort on your part. Mostly, you just have to be aware that this is what's going on. So if you have been asleep at the wheel and you didn't know that these tensor cores and things are out there, you might be a victim of copying and pasting in a terrible matrix multiply or some other weak implementation of an algorithm, not realizing that if you were using the canonical Magma implementation, you'd get that tremendous speed up. Some of the other things that these libraries use are what we call runtime dispatch. So they, like Intel, automatically enumerates every kind of CPU there is. And when you run the math kernel library on a particular target machine, it figures out all the little tiny details about that processor. So how large is the L1 cache? How large is the L2 cache? How large is the L3 cache? What is the NUMA topology? How many people here know what NUMA is? Okay, very small number. Well, we'll get to that. So understanding those minute hardware details, they can then detect what the target machine is, and they can launch a particular version of a routine that exactly matches that hardware. Going even further in the deep learning space, we have in NVIDIA's library something similar. There's a library called cuDNN, and it is massive. It's about 700 megabytes. It's a huge library, 700 megabytes. It encompasses not only all the different kinds of GPUs, but all the different shapes of tensors and matrices that you would ever want to operate on. And basically, by detecting a huge dispatch table and using the right piece of code for exactly the right thing, they are able to get a performance level that you would never achieve writing code yourself. There's no way. The search space is too great, and a single piece of code is not able to do it. So they do that with a giant lookup table. Another way that's sort of similar is what we call auto-tuners. Instead of dispatching to a fixed, already compiled chain of code, auto-tuners like FFTW uses, they basically look at the problem and the attributes of the problem that you've asked it to solve, and they do a test run. And so then they create what they call a plan. So if you say, I want to do a 64 by 64 by 64 3D FFT, I can call FFTW and say, this is the problem I really care about. I want you to run this over and over and over again. By computing this plan, FFTW can try a bunch of alternative code paths and say, well, I don't really know that much about the hardware. You know, it's usually the hardware vendors that have this runtime dispatch table because they know every chip they've ever built, right? They know everything about them. But open source library like FFTW, they don't really have that much information about the hardware, so they do it by a brute force test. They try a bunch of combinations, and then they figure out which one ran the fastest, and they return that as a plan. And then if you hold on to this plan, and then you call that library again in your application, you will get the peak performance that that library is able to achieve for that size or that characterization of problem. And so other libraries contain very complicated runtime systems. So like Magma from UT Knoxville, they have all these linear algebra solvers, and some of those problems are pretty sophisticated. And to implement those on a GPU or a hybrid system that contains a certain number of CPU cores and a certain number of GPUs is quite tricky. You are unlikely to beat them at doing this because they have dynamic work schedulers, directed to cyclic graph representations of the matrix work, and they can adapt their code at runtime to fit whatever hardware they're running on. It's very, very slick stuff. And so this is all technology that benefits you as a library user. So going back to, this is all great, but what does this mean for you? You have to be aware of how those things interact with your code. So one of the things I already described is like those auto-tuners or things that generate code on the fly. To do what they do, to give you that performance benefit, there is an upfront cost. You have to actually invoke them and say, here's the problem that I care about. And you have to give them that template problem and then say, all right, I'm going to use this over and over. That comes at a cost. It's kind of like starting your car and warming up the engine or something in the winter. You can't really go until after this auto-tuning or this JIT generation phase is over. Once it's over and it's paid for, you can amortize it over and over and over. But if you're only going to do something once, it's not going to pay off, right? So you have to be wary of that. You don't want to use auto-tuners or JIT generators if you're only going to do something once. There are special APIs in some of these BLAS libraries, for example. If I want to do some small 4x4 matrix operation, but I have millions of them to do, I showed you the performance towards the left hand of the chart is basically 0 for the small size problem. So one way they have learned to ameliorate that is to gather up millions or thousands of these small problems together, and using a small extension of the existing programming interface, you can use it as a caller, can provide them with a large number of these small problems, and they can then farm those out over all the compute units. So this is a much better way of utilizing large multi-core CPUs and the many-core GPUs that we have on state-of-the-art hardware. So just as an example, how many of you even realize that there's such a thing as sign costs? How many of you even knew that there was a library routine called sign costs? Okay, well, there is. And the reason why there's such a library routine is it turns out that in a lot of real codes, people call sine and cos on the same angle theta. Okay? I don't know if you've ever seen what's inside of these transcendental functions, but essentially half of the code is domain checking on the input value. So before you even get to the meat of calculating that value, there's all kinds of error checking. Is it a legal number? Is it an infinite? Is it a denormalized floating point number? All these different boundary conditions that they have to watch out for. And then finally, the last 3 lines of code is where the arithmetic, the magic actually happens. If you do that in a single call, you have almost doubled your throughput. And this is a trivial math library example. Now, Intel has taken that to the extreme, and they have what they call in math kernel library, they have vector versions of all the basic functions. So you can do something like sine or cos or sine cos, and you can send in a 10,000 element vector and do them all at once. So if you have a big enough need for something like that, that's something you can do. In the case of NVIDIA, if you're computing huge numbers of random numbers, they have random number generators that are batched. So they take, you can tell it, I need 5 megabytes of random numbers. You can get them all at once at a much higher performance than you would otherwise be able to achieve. And then sort of more mainstream examples would be FFTW, MKL, CUFT, and the other libraries. They provide things like batched FFTs, small matrices, all those things. And so I'll just give you an example. So this is a paper on Magma by our friends at UT Knoxville. So here, down at the very bottom, you see the CPU with 16 OpenMP threads, and you see 3 GPU versions. The green one is what you sort of normally expect, right? The performance is very bad towards the left hand of the chart. And as the problem size grows, why is it bad? It's because the GPU is a massively parallel processor, and if you give it a matrix of size, 4, there's no work. There's nothing for it to do. So it's not the GPU's fault. It's just that's how it is. So if I only give it one matrix at a time, that's what's going to happen. It's that green line there. It'll eventually catch up with that CPU and eventually surpass it. But you're using, for the first half of this chart, you're barely even scratching what the GPU is capable of, right? So the benefit of using a batched interface is now we're giving the GPU a lot more work right at the very beginning. So I may be doing tiny little matrices, but I might give them 1,000 of those matrices, or in this case, I think it was 400. So 400 little matrices at a time, and we're at least at 200 gigaflops. That's a heck of a lot better than being very nearly zero. So, the speed ups obtained from these batched interfaces are significant. Another example of that, so here's another one. What if I don't have 10,000 matrices that I can give all at once, but I know that over the course of my simulation, I'm going to do the same thing a huge number of times. Some libraries, like the latest Intel math kernel library, it has a just-in-time code generator, and that code generator will adapt to the particular problem size you request. So if you have a small little matrix, you can say, I want you to generate me a solver for this exact size. Now that, like I described earlier, costs you something. You're invoking a compiler. It's not instantaneous. It's going to generate some code, and then you can see if I do this using the JIT API, they get a huge performance gain for those small problem sizes, beyond what a canned library is capable of doing, or probably any other technology. JIT is probably, going forward, I'm very excited about things like JIT. Of course, GPUs are heavy users of JIT. I'm happy to see Intel use it. I think this is one of the areas where future library implementors will have a lot of performance to provide us, is by giving us really, truly specialized code exactly for the problem size you care about. So this is an example to show you another, to cover all the complexity of a modern piece of hardware. So this is actually not even that modern. This is about a 5 or 6 year old slide. And I just yanked it out of another deck because it shows, I guess what I'd say is a pretty typical machine today. Back then this was pretty exciting new stuff, right? Machine with 4 GPUs, 2 CPU sockets, a couple of PCI Express hubs and so on. But today, this looks an awful lot like the nodes that will be on the new NERSC machine, for example. They're almost exactly like this. So the first thing that's worth noting is this machine has 2 CPU sockets. So a bunch of you didn't know what NUMA is. NUMA is basically the observation that the way modern CPUs work is that they have their own separate memory banks. So this CPU 1 and CPU 2 have disjoint memory. And for one to read the memory of the other is slower than reading its own memory. And so if you're writing linear algebra routines and you're not aware of this, you might accidentally store a matrix in the memory that is slow for one of the processors to access. It might be smarter to replicate the matrix so that there's a local copy in both memory spaces and a bunch of other similar details. If you write stuff yourself, you would have to be aware of all those things. And of course, if we talk about the GPU, it's even more complicated because now I may have 4 different disjoint GPU memory spaces. They're attached by PCI Express buses and all this stuff. So, if you use a library, this problem is solved. Whoops, somehow we lost the page here. Not sure what happened there. Let me get that back. Maybe Keynote crashed or PowerPoint crashed on me. I'm not really sure. Yeah, I'm trying. There we go. We'll flip forward. It's a pretty simple talk, so we'll get there quickly, I hope. Sorry about that. All right. Oop, went too fast. Go back. All right, there we go. So, Another example of that is even if you knew exactly where your data was placed on the GPU, you might have several different choices. These are just the different communication speeds for certain size messages. And PowerPoint is, thank you for the crash notification, yes. All right, I guess you just didn't see that. So anyway, the different communication sizes and targets and communication schemes to and from the host or to and from one GPU to another, if you don't have a library to take care of that for you, that's something you have to deal with. So, these are all extra challenges. You're going to get to hear me talk about all this tomorrow, so I'm not going to go into any detail now, but basically libraries cover all this, so you get all this for free, and it's being done by people who this is all they work on all day long. They are experts in the particular hardware that they're targeting, and by using one of these libraries, this is a great way to get acceleration out of a GPU. That's really the starting point. So if you know nothing about GPUs, and you want to dip your toe in the water, the first thing to do is just go take one of your existing subroutine or math libraries and replace the run-of-the-mill library you've been using with a GPU variant of the same thing and see what performance you get. Now there's a bunch of caveats, right? Because these GPUs are at the end of a wet string, that wet string being this really slow PCI Express bus. The memory system on a GPU, state-of-the-art GPUs are 600 gigabytes per second to as much as 900 some gigabytes per second. PCI Express is 12, okay? So you have to be aware of that. You want to keep most of your work on the GPU, so you have to think about this when you're using whatever library. It may be less important what subroutines you're calling than which memory those subroutines are accessing. If you're calling some linear algebra solver and the memory is already on the GPU, that may matter a lot more than the finer points of which exact solver variant you used, because that memory performance is probably going to be dominant for you. Some of the things you have to watch out for with libraries is, they're not always free. Sometimes you have to restructure your code. They may demand that your data be organized in a very specific way. The layout of the programming interface may be such that you are not able to get the same vectorization or the same loop unrolling or the same inlining that would have been possible if you had implemented something inline yourself. So that there are some rare cases, if you really know what you're doing, you can often get better performance by not using a library, but you have to, all the stuff that I just told you, everything you heard from the beginning to now, you take that responsibility on your own shoulders. But if what you're after is, the fastest possible performance, that may be the right choice. Another thing you have to watch out for is when you take a library on, you're sort of taking its baggage with you. It's like a bad relationship, okay? If you get involved with a library that's got a bunch of problems on some hardware platform, or it creates difficulties for your end users. A lot of my users would already tell you that the software I develop is hard to compile because it has a lot of dependencies. I do use a lot of libraries, and even I don't feel like it's that many compared to something, a lot of the other tools like mine use far more than I do. But those are a hindrance to an average scientist who's they're not nearly as technically capable as the people in this audience. Most of them have never compiled software. They don't want to. They just want to deploy it. But if you have an MPI code, by and large, you have to compile from source. That's the nature of MPI. We don't really have an MPI binary compatibility interface. So that's the world we live in. If you know something about the domain of input for your math routine, you can get higher performance than the general math library function. So I told you sine and cosine, for example, spend a lot of their time checking the input parameter to make sure it's legal and valid and so on. If you know that your parameter falls in a very specific subrange, you could almost double the performance over a typical math library implementation. And so I've actually done that a number of times where I took a conventional math library routine, and because I know that either I can get away with a simpler approximation or that for some other reason another mathematical term dominates some equation and I only need a certain limited finite precision, I can write my own routine that greatly outperforms what a vendor-provided library would be able to do. And this gets more particularly interesting if the math library routine is the dominant place where you spend your time in some very tight loop. So I'll show you such an example. And that's an interesting issue because function calls are typically an inhibitor to vectorization. So if you use the Intel compilers, for example, they can auto-vectorize code and make use of the vector units on state-of-the-art CPUs. But if you have the wrong kind of math library or subroutine call in the midst of one of your loops, they will say, no, I can't deal with that. And they are incapable of then vectorizing that. So to deal with that, you would have to do something special. So just as an example, this is a little molecular orbital visualization loop for quantum chemistry visualization. The main thing that costs the runtime in this entire multiply nested loop structure is that exponential call in the center there in the white. So that is by far the most floating point intensive part of the code, and because it's in a bunch of multiply nested loops, its cost is very high. Because it is a math library call, a lot of compilers are totally incapable of vectorizing this code, so it means it's running as scalar code, no vector unit use at all, and the only benefit on the CPU would be running on multiple cores. So that's something, but it's far from what I want. And because I know that all of the input values are negative, a large part of the input domain is excluded. And that's it. If you go look in CFEs or other math libraries at what goes on inside of an exponential routine, you can yank all of that out and make that code substantially faster. So I did exactly that. And for an exponential routine, I can get easily a factor of 10 over anything that any of the vendors have, including their vector versions, because I can use an approximation, I can use fewer terms in a Taylor series, things like that. So although I, of course, tell you all, use libraries, it is good for you to know what's inside them. And so that's why I showed CFEs at the beginning. I love CFEs because you should have a feel for what is this black box? What's inside there? What am I paying for that I didn't realize it was costing me? If you have a special case like this where some single thing dominates your runtime, you can then do something special and gain a tremendous amount of performance. So I'll finish up. Libraries aren't just for computing. They're also for things like I/O. I/O is a huge part of what we do. I won't belabor it, but basically two of the most popular I/O libraries that are very general purpose and are well suited to HPC are NetCDF and HDF5. Actually, the latest versions of a NetCDF are basically built on top of HDF5 as a foundation. And what they really do, they have bindings for every language you'd ever care to use. They have great documentation, and they are well suited for HPC codes. Basically, they're ideal for things like storing time series data, binary blobs of large scalar fields, vector fields, everything you'd ever want. They have compression. They will do endianness conversion. Probably a lot of people here don't even know what that means. How many people know what endianism is? Yeah, okay, so not many of you. It's because you've all been using x86 hardware. But if you go and run on some other hardware like a different ARM chip or something like that, or a Spark chip someday, maybe a Japanese K machine, you would soon learn that there's other endianisms than just what we use on x86. And so that's important. When you're reading and writing files, the order of bytes can be automatically converted to the machine you're using. And there are also libraries for things like HPC Graphics and Visualization, so tools like VTK. So VTK is both a standalone tool, but you can use it as a library. There are multi-core versions of it. Things for graphics like EGL and Vulkan work just as well on a supercomputer as they do on a desktop machine. And then there are lots of libraries for much higher end image rendering and visualization. So examples of those are Osprey and Optics, and VizRTX is a new visualization framework. So all these things are out there. There are, of course, libraries for graph analytics and lots of other types of statistical information. When they're open source, it's good to look inside under the hood so you know what you're getting. I would say there are a few do's and don'ts. Do use the standard interoperable library APIs. Even if you end up using something specialized later, it's good to retain compatibility in your application software. Even though I have done lots of things and I've rewritten my own math library routines when it was necessary, I still keep backwards compatibility. It makes it easy for me to port to a new machine in a hurry. Use libraries to support accelerators. That should be your first step in using a GPU before you write any of your own code. Use high-level APIs. So if you have a choice between just using BLAS versus using a higher-level solver like what you find in LawPack, use what's in LawPack. Don't roll your own yourself. The reason is you're giving the runtime system of the solver more flexibility. It can make more choices that are beneficial either for accuracy or performance. Do use things like the batched APIs, do use auto-tuning and JIT. Just be aware that those things have costs and they're not free, and so you want to use them when it makes sense and not when it doesn't. So I would say don't use a library without considering what obstacles it might present to an end user who has to compile your code from source. And I would say watch out for libraries that harm or lead you astray in terms of your long-term portability of your software. Leave yourself an out because they say the average code outlasts the hardware it was written on by 10 to 20 years. That's a significant amount of time. And so, don't run with the same library indefinitely. Once every so many years, you should go do a bake-off. Because these numbers, they change. Like I've shown you a couple of snapshots that are just off the web from the last week, but the fact is if you go back and you go to one of those other BLAS vendors' websites, they probably have a new number that they just put out in the last week. And so it's a game of leapfrog. For every improvement one vendor or implementer makes, somebody else will mirror that improvement in their own code before too long. So keep your eyes open because there's a lot of activity here with libraries. DOE has put millions and millions of dollars into exascale computing, and a significant component therein has been library and framework development. So there's never been a better time for reevaluating what libraries exist than there is now. There's a lot of activity there. It's not all just linear algebra. And of course, keep your eyes open for the things that the hardware vendors are doing. Hardware is changing really fast. If you went back 2 years ago, nobody had even conceived of having tensor cores. Or if I asked you an hour ago, do you think that there's an underutilized functional unit on a GPU that you could just use for free that would give you another factor of 4 on linear algebra? You'd be like, what? Yeah, so you got to keep your eyes open for those change. And now I'll take your questions. Is Scott or somebody here to field the questions for me?
Yes, I will do that.
Very good.
First of all, thank you for the presentation. So we have a few questions online.
Sure.
What's the performance difference between CUDA runtime compiler versus the standard static CUDA compiler?
They're very similar. So I've used NVRTC. So the NVRTC is a JIT compiler that you can use with CUDA source code. So you can have an algorithm that your own application sort of generates CUDA source code at runtime. So for example, I'll show you this example. I have done that with this actually. This is a great example. So I can compile this with the CUDA compiler, or I could compile this at runtime. Why would I do that? Because the actual implementation of this code, the trip counts in the innermost loops of this code tend to be small, like maybe 6 iterations. That means there's a significant amount of loop overhead, control overhead. If I generate code for that, I can actually speed up this code by almost a factor of 2 by eliminating the loop and have it be completely unrolled. So by doing that in a JIT compiler, you can get a factor of 2 in performance. So I would say I have done that benchmark, and I would say in my experience, the NVRTC for my code was basically the same performance as what I had with the batch mode compilers. I haven't retested that recently, but that's how it was back, let's say 3 years ago. But that was also, I had done as much as I could to make that code easy for the compiler to optimize. So.
Thank you. So this question I actually had a second part. What could be a reason for error launching CUDA compiler error?
Oh gosh, we'll have to take that one offline.
Okay.
Debugging, I can't do real time at the podium, but we'll talk about that in a minute.
Okay.
Next.
So, any comments about Cocos, Raja, Boast?
Well, Boost. What was the last one?
Boast, B-O-A.
I don't know Boast, so it sounds cool. No, Cocos and Raja are, I guess I would view them not so much as libraries, but rather software development compiler frameworks. So the idea of Cocos and Raja is you express your software with a different syntax, and basically, as an alternative to writing CUDA or something like that, they generate code for multi-core CPUs or GPU backends. I don't really know. Here's an interesting question I would pose to the developers of Cocos and Raja, and I don't know the answer to it. How are they for writing libraries? That's a good question. And how composable are they and their runtime systems with other stuff? So I know people write applications in Cocos and Raja, but I don't know if anybody writes libraries in Cocos and Raja, and I don't know what complexities that might bring up. But those are really compiler runtime type things and not so much libraries. So we'll take that offline if there's further questions in that space.
We do have one more question.
Sure. Yeah,
okay.
Go ahead.
Can you comment on how to test whether a given library is thread safe? What exactly does this mean?
Thread safety basically means, does that library have any hidden internal state that is not observable to the outside, that is not expressly managed by the programmer? So, for example, there were, like a great example is the old C random number generator, RAND, right? There's two APIs to the standard C random number generator. There's SRAND, which seeds the generator, and there's RAND, which queries the generator. Well, unbeknownst to the average developer, SRAND and RAND basically hide a state vector that's in a global variable inside the C library. So the problem is if two threads call RAND and SRAND at the same time, or they call them in independent threads, you have an implicit race condition, because one might be resetting the seed while the other's querying it, and or one might be incrementing or reevaluating the next random number while the other's fetching it, and they can corrupt each other's random number streams. So to avoid that, they changed the random number interface and made it a what's so-called thread-safe reentrant version like RAND-R. So there are some _R functions for old C library APIs that are now deprecated because they were thread unsafe. So anytime you have something, MPI is another example. MPI, as originally written, is not thread safe. Why? Because there are hidden internal state inside of the MPI library that you as a programmer cannot see, cannot save and restore, and have no means to control. And so as Galen said in the last talk, when you use MPI in combination with threads, the MPI libraries have a special enumeration or a special macro that you pass in that when you initialize MPI to make it aware of how you're going to use it. And what that influences is it tells the MPI library either it needs to do extra bookkeeping for itself to save and restore its own internal state on every single call. So if you say MPI send and I've told it I'm using threads, the first thing it has to do is fetch what they call thread-specific data to get its internal state for that endpoint, and it will then go look that up and say, okay, now I can go do my MPI send. If you had told it that you were running single-threaded, it gets to skip doing that. So it's a little bit faster to run something that is thread unsafe in a single thread than to run something that's thread safe. Thread safety usually comes with it's either an additional set of parameters or the requirement that the user manage the state vector, or if it's hidden from you, you're going to pay a per API call cost. It's very small, but it's not zero. And so that's why there's this special initialization for MPI. Both of those are examples of thread, libraries that were written prior to consideration of thread safety.
Right. Thank you. That was the last question. I would encourage everyone to continue to post their questions on Slack. And with that, let's thank John for a wonderful presentation. And our next session starts in 20 minutes. Thank you, John.